Hey guys, so today we're going to discuss the power rule, and we're going to use it to compute some derivatives. So we're going to do some examples. I'll also do examples in a tutorial video afterwards, much more complicated examples, I guess. So the power rule is a very important rule. You'll be using it a lot, so you got to get familiar with it. It's probably the rule that you'll be using the most. So especially in higher level calculus, because they tend to put easier functions because they're testing different skills. So let's get started. So why do we have these rules? Well, using the limit definition of the derivative can get very tedious and messy as the functions get more complex. So we've derived some rules that will help us simplify our calculations and make it much faster and much neater to compute the derivatives of more complex functions. Well, in this video, we're going to discuss one of the simplest rules, which is the power rule. However, before we get into that, I just want to discuss the derivative of a constant function. Consider a function f of x is equal to 6. So let's find the derivative of this. So y prime, well, using the limit definition of the derivative, you can just say, limit as h approaches 0 of f of x plus h minus f of x all over h. Well, notice that the function has no x terms. It's just 6. So this makes f of x plus h, turns out, is just, got to write our limit as h approaches 0, is just 6. And obviously f of x is just 6. So 6 minus 6 all over h. Meaning, well, obviously this is just 0. The limit, computing the limit just gives us 0. Okay, what if this is just a coincidence? Well, let's consider another function. F of x is equal to 10 to the 8. Well, using our limit definition, as limit as h approaches 0 of f of x plus h minus f of x all over h, what we get is, well, f of x plus h, there are no x terms, so all we get is 10 to the 8 minus, well, f of x is 10 to the 8 all over h. We end up getting 0 again. Well, forgot this. As h approaches 0, we'd just end up getting 0 again. So, turns out, I'm going to erase this. Turns out that the derivative of a constant is 0. It's always 0. So you got to keep this in your head because this is very important. You'll use it a lot. The derivative of a constant is 0, but let's see why. Let's get a visual idea of this. So I'm going to erase all I've wrote here. So let's get rid of this. And let's see why. Let's draw a graph. Let's say we got our function f of x is equal to 6. Let's say this is f of x equal to 6. So a good skill to have in calculus, obviously, is to be able to visualize different graphs of different functions. Get this rough idea in your head. And in this case, it's quite easy. We've seen this before, probably when you guys just started, with linear functions. And this is not a very hard function to, visualize. So looking at this, we recall that the derivative gives us the slope of a tangent line. Well, this is just a horizontal line, so the slope of the tangent line at any point here is horizontal. And so what is the slope of a horizontal line? Well, the slope of a horizontal line is just 0. The rate of change in y with respect to x is 0. Therefore, the derivative is 0 for a constant function. Makes sense. So I want you guys to obviously know this. This is basically just a thing that you should just know when you're taking derivatives, that when a constant comes up, well, the derivative of it is 0. So let's continue on. Let's get into the power rule. So the power rule is the power rule is a very important rule, like I said. And what the power rule is, I'm just going to write it down right here, is that the power rule says, let's have some function f of x. Say f of x is equal to x to the n. Well, the derivative of this, f prime of x, is n times x to the power of n minus 1. So what does this mean? Let's kind of translate this to plain English. Well, this is just saying, what this is saying is to bring down this exponent and multiply it. But at the same time, minus 1 from this exponent up here. So what you're doing is you're bringing down this exponent, and then you're also minusing 1 from the exponent up here, and then you're multiplying these two. That's what it's saying. Now, it's not very hard to grasp. You can see, and when we apply it, you get a better sense of it. Sometimes writing it, you see all these, letters, and you kind of get thrown off. So when we do the examples, you'll get a hang of it. And important thing in calculus is to do a lot of practice questions, because, well, they really help you, master these skills, and you're gonna be using them a lot if you continue on in calculus, physics, and such. So, well, this power rule didn't just fall from the sky. It's not just a magic rule that popped up out of nowhere. Well, we can actually go back. We can actually get it by going back to the limit definition of the derivative. So I'm just going to erase this real quick, and we'll bring it up again. So let's look back at the limit definition of the derivative. Well, we know f of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Well, let's consider some function f of x. Actually, I'll write this up here. F of x is equal to x to the n. So let's use the limit definition and compute this. So what do we get? We get f prime of x is equal to the limit as h approaches 0. And we got this f of x plus h. So what this turns out to be is x plus h to the n. And f of x itself is just, oh, what's this? Okay, it is just x to the n all over h. Well, how do we expand this? Well, we expand this using the binomial theorem. Well, what does this turn out to be then? Well, this turns out to be a limit as h approaches 0. This turns out to be x to the n plus n minus 1 h n minus 1 all over 2 x and minus 2 h squared. And because we have a lot of terms, we're going to do this dot dot dot, and we're going to put x nx h to the n minus 1 plus h to the n, and that's just in brackets. That's just expanding this part. So we still got our minus x to the n at the end, and this is all over h. Well, we notice some cancellations. Always looking for cancellations when we use the limit definition of the derivative, and we see them. X to the n, that's gone. And we got these h terms, h, and we got more cancellations here. in terms of the h's. So what we realize is that we have a bunch of these h terms in here too. Is that what we get is the limit as h approaches 0, and recall right here, there's no h term now here because, well, we canceled it out. We get nx to the n minus 1 plus a bunch of terms with h. Well, as the limit as h approaches 0, these terms all become 0. They all disappear. So what are we left with? Well, what we're left with is just f prime of x is just n x to the n minus 1. And as we saw before, this is our power rule. Cool. So, well, now we got this cool new fancy rule. Well, how do we use it? Well, let's do some examples. First example, we're going to start real easy. And we're going to start with f of x is just equal to, well, x. Okay, so let's look at our power rule. F prime of x equal to, well, n x to the n minus 1. So let's look at our original function. F of x is equal to x, and I'm trying to find the derivative. So I'm trying to find the derivative f prime of x. In this case, looking at f of x is equal to x, what is the exponent on x? Well, the exponent on x here is just 1. So, computing this, what we're going to do, remember, if you think about this in plain English, is that we just bring down the exponent and then we minus 1 from the exponent. So let's bring down the exponent. Well, we got 1. Got 1 right here in brackets. And we got x. So what do we do now? We got the exponent 1 and we minus 1 from it. So, well, what does this come out to? Well, this comes out to 1 times x to the 1 minus 1, and 1 minus 1 is 0. So we have 1 times x to the 0. Well, what's x to the 0? Well, x to the 0 is just 1. So all we are left with is 1 times 1. And what's 1 times 1? It's just 1. And we can easily see this by drawing a graph. Is that we got our function x right here, f of x is equal to x, going through the origin. Well, what's the slope of this? Well, the slope of this function, x, f of x equals x, is just 1. And that's what we got, the derivative. It's because the slope is always 1, we got the derivative, it's just 1. So that's a really easy example. Let's go on to something just a little more complicated. Not too complicated, pretty easy, kind of similar. So f of x is equal to x squared. Now, you know, we've seen this a bunch of times using the limit definition of the derivative. So in this case, f of x, let's write down our rule. So when you get started with this stuff, it's good to write down the rule. You'll get a hang of it. It'll almost become, you know, like you were just born to take derivatives. It'll just become like that once you get a lot of practice. So let's write down our rule. We're starting real slow. So we got n x to the n minus 1. So let's follow this rule. What is it saying? Well, what this rule is saying is, well, bring down the exponent. So we got 2 times, we got x, and then we got that exponent, because n is 2 here. Remember that. Look at it. N is 2. We got n. This is saying n minus 1, so 2 minus 1. Well, what is this? Well, this just turns out to be, let's simplify this. We got 2 times x. What's 2 minus 1? It's 1. It's just x to the 1. And then this is just 2x. Real simple, real easy, and we discussed in the limit definition of the derivative that because x squared, let's say, is a parabola actually, well, the slope of the tangent line changes at different points on this parabola. So this gives us a function that will tell us the slope of the tangent line at different x values on this parabola. So, well, does this match with what we found in the limit definition of the derivative? Using the limit definition of the derivative, well, let's see. F of x is equal to x squared. Let's use the limit definition of the derivative. Limit as h approaches 0 of f of x plus h minus f of x all over h, and then this is just limit. Remember, our f of x plus h is x plus h squared minus x squared all over h. Expanding this, the limit as h approaches 0, we just get x squared plus 2xh plus h squared minus x squared all over h. And we see the cancellations right here. And we see that. And what are we left with in the end? We're just left with 2x. Well, this matches. Our derivative using the power rule and our derivative using the limit definition is the same. They match. Okay, so let's try a little bit more complicated example. So like I said, I've said this a lot of times, is that you gotta have strong pre-calc skills. So let's consider our function is f of x is root x. Okay, so this is at first look, this might seem a little complicated. Well, I said have strong pre-calc skills. So if you have strong pre-calc skills, you can right off the bat see that if f of x is root x, well, this can also be written as x to the half. Write that a little better. X to the half, right? The root x is just x to the 1/2. So let's use our our rule. So we got f prime of x is equal to n x to the n minus 1. Well, in this case, what do we get? Well, we bring down the half, right? Multiply it, and we get x, and we do 1/2 minus 1. Right? We just stick to the rule. We're just doing what it says, right? So what does this come out to? Well, this comes out to, we got 1/2 times x to the negative half, because 1/2 minus 1 is negative 1 over 2. So at the end of the day, if we really want to simplify this, all we get is 1 over 2 root x. This is our derivative. 1 over 2 root x, right? Because this just becomes 1 over root x, and then multiplied by 1/2, and you just get this. So, like I said, strong pre-calc skills, to be able to recognize that, root x is just x to the half. And it's very important that you are able to instantly see this, especially as you go deeper and deeper into calculus. So let's do a slightly more complicated but similar example. So let's say f of x is equal to the 5th root of x. Okay, strong pre-calc skills. Remember that this can be written as an exponent. So x to the 1/5. So you can say x to the power of 0.2, x to the 1/5. So using our power rule, which says f prime of x is n x to the n minus 1, we just follow the rule. It's saying, bring down the exponent, which is 1/5, times x to the 1/5 minus 1. And what does this come out to? Well, this comes out to 1/5 times x to the negative 4/5. Easy. Real easy. But it's easy if you have these pre-calc skills, this ability to recognize that this can be written as an exponent and then to write it as an exponent. That's a very important skill to have. So let's move on to, could say maybe a comparable example, but it's a little different. So f of x, and this is 1 over x. And we computed this along with root x in the limit definition of the derivative section, I believe. So, well, how do we do this? Well, it's 1 over x, and again, strong pre-calc skills. Your ability to recognize that 1 over x can be written as an exponent. X can be written as that, x to the power of -1. So ability to recognize that. Now 1 over x is x to the -1. Well, now that f of x is written as x to the -1, well, this is quite easy. Just follow our rule. F prime of x is equal to x, n, x to the n minus 1. And then this, well, just following the rule, bring down -1. So we got that. And we got x, -1, and we just minus 1 from that. And what do we get? Well, we just get -1, x to the -2. And simplifying this, well, we just get -1 over x squared. Nothing complicated. Pretty easy. So, well, let's take a second derivative. Let me erase this. Let's take the second derivative. So, well, we got our first derivative. I'm just going to rewrite this up here. We got our first derivative here, right? So we got f prime of x is -1 over x squared. So let's take our second derivative. Well, we recognize, because we simplified this, well, we recognize, again, strong pre-calc skills to be, rewrite the function. Well, we recognize this as -x to the -2, right? So taking the second derivative, we do the same thing. We got n x to the n minus 1. Well, in this case, n is equal to -2. So we bring down -2, so we got -1 times -2, and then we got x to the power of -2 minus 1. Well, simplifying this, the second derivative just comes out to be, what's -1 times -2? Well, it's just +2. And we have x, we got -2 minus 1, which is just -3. Cool, we got our second derivative. Easy. Okay, why don't we go for a third derivative? So I'm going to erase this. Let's try to find the third derivative of f of x is equal to 1 over x. Let's find the third derivative. So we get our second derivative here, right? So we get our second derivative, and that is 2x to the 2 times x to the -3. And okay, we want our third derivative. So we're just going to look at that rule. N times x to the n minus 1. And what's this come out to? Well, n is -3, we can see. So bring down -3. So we got 2 times -3 x to the -3 minus 1. Okay, so let's simplify this. Well, what's 2 times -3? Well, it's -6. And we got x. So what's -3 minus 1? Well, it's just -4. Ta-da, we got our third derivative. So you can see as you keep bringing down exponents, we obviously have to multiply by, you know, whatever factor was already there, whatever, you know, coefficient's already there, right? Keep bringing it down, we multiply and we simplify. I'll do more examples in the tutorial. Like I said, more complex examples, but here I'm just giving you this idea of, you're just using the rule on pretty easy functions. It's just that you need to be able to recognize and be able to rewrite things like, root x or 1 over x, and then use the power rule to compute the derivative. So before I end this video, I want to talk about something very, very, very important. And that is, well, sometimes students, if they get something like, let's say f of x is equal to e to the x, they try to apply the power rule, and that is wrong. F prime of x of e to the x is not x e to the x minus 1. No. The power rule, rewriting the power rule, say this is the power rule, n x to the n minus 1. I'm going to write this. Recall that n is a constant, x is a variable. Looking here, the base of this exponent is a constant. E is a constant, about approximately 2.71, going on. E is not a variable. X is. It's a big difference here. Here, the variable is the base. Here, a constant is the base. Functions like f of x is equal to, 5 to the power of x. The derivative of this is not x 5 to the x minus 1. We will discuss how to take derivatives of these in a different video, in a later video, pretty soon actually. But recall, you really gotta, see this, that you can't apply the power rule when the base is a constant and then the exponent is a variable. You do not apply the power rule in that case. And that's a mistake a lot of people make, is that they start applying the power rule to things like e to the x or 5 to the x or anything like that. You can't do that. That's not how it works. The power rule only applies if, got x, you get the base is some variable, and then you got some, some power, well, sorry. You got x, and then n is just some constant. So be aware of that. Variable, constant. In this case, this is a constant. This is a variable. And with practice, you'll get used to this. It'll be very easy to, see these differences, especially in later videos when we discuss this. So be aware of this. Do not make this mistake. It is a fatal error, especially on an exam or an assignment. It will lead you to the wrong answer. And frankly, just don't make this mistake. Really, really keep your eye out for this and keep your mind open when you're working. Don't make this mistake. So we're going to end the video here today, and in the next video I'll do a tutorial with some more complicated examples using the power rule. So